I'm working on these big projects right now, but my PhD was entirely theoretical, where I looked at concepts about the Big Bang, the expansion of the universe, and sort of misconceptions about the Big Bang, and things about the entropy of cosmological event horizons. So cosmological event horizons have an entropy similar to the entropy of the event horizons of black holes. So every once in a while, when asked to give a talk, I actually return a little bit to my roots and talk a bit about these conceptual questions. So I've chosen to do that today. So I hope you like it. Some of the things that I'm going to talk about, I know if you're a cosmologist, you may know lots of these, and some of them may be obvious, some of them, but I find that even for cosmologists, we're working in the field, but we often don't even think about some of these questions. So hopefully there's a little bit here for everybody. I'm going to try and make this a little bit interactive. Usually when I give this kind of talk, I'm in the room with people, I can see people's faces, I have some feedback of whether you're bored or excited. That's hard to do, and it's hard to see everybody. So thanks, Mike. But I thought I'd make it a little bit interactive. So I don't know if anyone's used Slido before, but if you can jump onto Slido, if you have a phone or whatever, if you go to www.slido.com, this address at the top here, and sign into the meeting called Cosmo, then I will ask some questions there. So go ahead and jump on there if you can at the moment. And I'll put a generic question up just to see if you can see the poll. Hopefully, if you're there, you can see the poll. You can answer A if you think that 5 a.m. is too early to give talks, and answer B if you think that it's a fantastic time, just to see if you're getting online successfully. Okay, I'm getting lots of responses.
I see something called generic question, and I see cosmic confusion. So
yeah, perfect. So that's perfect. That's all working. So if you can see the polls and just see it. And if I stop that, you might be able to see the answer. Oh, no, you can't see the answer. I'll just have to tell you what the answer is. Cool. Okay, powering on. So I've written a whole bunch of papers that are related to some of these questions. So I will, a lot of the things that I'm talking about are in some of these papers. And I wrote a couple of popular versions of some of these for Scientific American as well. So we'll put that back up at the end if you're interested. The first question for you guys, in our universe right now, we have velocity is the Hubble lemaitre parameter times distance. Is h, we live in an accelerating universe, and h naught is the expansion rate at the current day. Is h increasing, decreasing, or constant? So there's a poll for you. Hopefully you can see that. Okay, so I've got 20 responses at this stage. And I'm trying to figure out how I can show you the poll. I'm going to stop in a couple of seconds because that's sort of a good sampling of everybody. If you didn't get on Slido before, the link every time I ask a question will be at the bottom right of the page. So the answers that I had was that 60% said that it was increasing, 20% it was decreasing, and 20% said it was constant. Okay, so the majority think it's increasing. Okay, we'll get back to this question in a moment. So in this equation, is velocity is Hubble constants times distance? Do you think this is derived from general relativity? Is it required by symmetry? Is it an empirical relation, or is it all of the above? But I've just made this one a generic question Whoops, I need to clear that somehow. Cool. So answer A, B, C, or D for this one. So some of these questions that I'm going to give you are deliberately ambiguous or don't have necessarily a clear answer because some of them are intended to spark thought/discussion as opposed to be completely 100% determined at a single answer. Okay, so far with 20 responses, we have 55% say it's all of the above, and 35% say it's answer C. So a few more are now, since I've told you that, a few more are saying all of the above. But let's go in and have a look at the answers to those two initial questions. Okay, so I would argue that Hubble's law is required by symmetry primarily. We're familiar with the Friedmann-Lemaitre-Robinson-Walker metric here, which is the general metric for an expanding isotropic homogeneous universe. It doesn't require general relativity necessarily. If you take out the dt here and stuff, anything that's homogeneous and isotropic, if you want it to stay that way, then V has to equal HD. Otherwise, you lose homogeneity and isotropy. So it's a requirement of the symmetry that's true. And it's not, you don't actually need the Einstein equations at all to do it. You just need sort of that symmetry, and you can derive it from this metric. So to do so, in order to answer the first of our questions, you can note that if you just look along a constant time slice, so dt equals 0, and just look radially, so you have no angular terms in your metric, the terms that you're left with are these ones here. And once you integrate that, you get that the distance is the scale factor r times the co-moving coordinate. I use r when it has dimensions and a when I put the dimensions in the co-moving distance. So for co-moving objects, if you differentiate this, you just get the velocity is the rate of change of scale factor times the co-moving coordinate. This is for co-moving objects. And of course, then if you divide by r and multiply by r, you can see that you get velocity, the term on the right becomes distance again, and you get velocity as Hubble's constant times distance, Hubble-Lemaitre constant times distance. And you can see h is defined to be r dot on r. Whoops. You can see from this equation that the Hubble parameter has to be the rate of change of scale factor divided by the scale factor. And as a result, even in our accelerating universe right now, h is decreasing with time. So the 60% said it was increasing, and often that's the assumption. If we're in an accelerating universe and h naught is the current expansion rate, then h should be going up with time, right? But no, because of this definition here, sure, right now, and when scale factor is r naught, and r naught is and the scale factor, once you've normalized it, is 1 at the present day, that becomes just the present expansion rate of the universe, a dot. But in general, here you've got the numerator is increasing in an accelerating universe, but the denominator is increasing faster. And so h actually goes down with time. And you can also look at that from looking at Friedmann's equation. If you have h squared is h naught squared times some function, for example, omega matter, times scale factor to the -3, you can see again that h would go down with time or as scale factor increases there. In fact, h is only constant when the expansion becomes exponential. So in the infinite future for us, if we're in a lambda CDM universe, the expansion will become exponential, and will end up with scale factor with h is equal to h naught all the time, where h naught is the value in the exponent. But that's only if you're accelerating dramatically. If you're accelerating faster than exponential, then h will go down with time. So I actually asked this as a really mean interview question once when I was interviewing postdocs, and it was just a good sort of thing to see how people think about the problem and how they figure out what it might be. Not many people got it right. if you want to think about this more intuitively, just with a picture, you can see why h goes down with time. This is just a simple space-time diagram with time going vertically and distance horizontally. And if you look at this along a constant distance, at a particular distance, the velocity of the galaxies is going down with time. So if you start here, you can see that at this distance, early on, there was fast recession because only the fast galaxies had managed to make it out that far at early times. But as time goes on, you end up with, at that same distance, the recession velocity has decreased. And so you can see just in a non-accelerating universe, intuitively using this diagram, that you would have h going down with time because the velocity at a particular distance goes down with time. Does that make sense? Hopefully. I can't see your reactions. I can see one thumbs up. So that's the first sort of summary there. Okay, so what happens when distance is greater than speed of light divided by the Hubble parameter? Now, I'll just stop the previous question and ask this one. So this was actually the question that sparked my my honors thesis, like my first research into astronomy when I was an undergrad, because my supervisor at the time handed me one paper that said, this says recession velocities can exceed the speed of light, and this one says they can't. Which one is true? And that became my first undergrad project. The answer had been known since the 1930s, but this was in the late 1990s. And for the first time, observations were routinely getting to redshifts or distances where this question was actually relevant, and people had started to do it incorrectly. So the questions for you, you need to apply relativistic corrections to the velocity. Recession velocities exceed the speed of light, and we can observe galaxies that are receding faster than the speed of light. Recession velocities exceed the speed of light, but they're not observable, so they're not super relevant for us. It is useful for me definitely to see the answers to these polls coming in, because it's cool to see what people think. If I was in the room, I'd get you to put hands up, but this way you can more anonymously answer anyway, and not be influenced by what you see people around you doing. Okay, so with 25 responses so far, I've got 46% say C is the correct answer. Recession velocities exceed the speed of light, but we can't see them. 35% said B, and 19% said A, that you need relativistic corrections. So none of the answers are above 50% here, but the most popular is C. Okay, so let's have a look at the answer. So here is velocity versus redshift. The plot on the left is the velocity at the current day as a function of redshift. You'll notice, that here's the line for speed of light. If you're in special relativity, you see that the line sort of asymptotes to speed of light as expected. If you use the approximation velocity as speed of light times redshift, you get this dotted line. And sort of the range of potentially plausible universes that we could live in is sort of this gray band, where you can see that the velocities do indeed exceed the speed of light, and at redshifts that we can see. This is the orange line in the middle here is the universe that we think we live in, a universe with matter density about 0.3, cosmological constant about 0.7, and you actually don't need to know much else for this. And if you look at the velocities that things had at the time of emission of the light that we're now seeing, the velocities exceed the speed of light back then even more dramatically. So this goes up to 50 times the speed of light once you get to a redshift of 1,000. You're at sort of 10 times the speed of light at redshift of 700 or 70 or something like that. So what's going on? most of the people who answered were comfortable with the fact that things could go faster than the speed of light, but less comfortable with the fact that you can see them. So let's have a look at how this all works. And there were still 20% who said that things couldn't go faster than the speed of light, or you needed special relativistic corrections. So I'll answer that while answering this other question as well. So if we shine a light, or like look at the light from our galaxy, how far is that light going to reach? Is it going to go an infinite distance, a finite distance, or some other distance? I don't know what the difference between those two could be, but will it go an infinite distance or a finite distance? This one's potentially ambiguous as well, actually. Cool. So with 20 responses, or with 18 responses, oh, it was a dead heat. Oh, it's back to a dead heat. Oh, with 25%, it's gone. The infinite distance is slightly higher than the finite distance, but they're 46%. Oh, they're back at a dead heat, 44% each. So this is well, let's have a look, see what we see. Okay, so to explain first why things can go faster than the speed of light, why the expansion of the universe can be faster than the speed of light, let's have a look at the metric again. So if recall, we had the bit before where if you're looking at, if you are looking along a constant time, these are the metric that you have left. And so a distance is a scale factor times co-moving coordinate. But if you, before we just looked at co-moving objects, if you allow motion that's through space as well as the expansion of space, then you get the second term where you have rate of change of co-moving coordinate as well. So you have your total velocity is made up of the part that's the h times d and the part that's the peculiar velocity. Now, what does light do? If we recall our relativity, light travels along null geodesics.
Sorry, can I object at this point, or should I wait? Yep.
Go ahead.
Yes, I was just going to say, I mean, this definition of velocity is kind of arbitrary. And in fact, I mean, there is no such thing as, I mean, scalar velocity in general relativity. So it's, I mean, you kind of take this distance, which is also kind of arbitrary, and then take its derivative, which, I mean, sounds reasonable, but I don't think it's really, I mean, it's a unique definition, it's a coordinate independent definition.
Absolutely.
So that was
Thank you very much for asking that question.
Okay.
I thoroughly agree and was definitely going to address that. I probably should address it earlier on, because velocity, I should have actually addressed it early on, because the velocity that I'm talking about is the velocity that appears in Hubble's law, and the velocity, the peculiar velocity, being the distance relative to the infinitesimal special relativistic frame, the Minkowski frame at that point. So that is an excellent point. And so velocity is definitely a coordinate dependent property, whereas redshift is measurable and coordinate independent. And so I would advocate, when doing cosmology, to avoid talking about velocity as much as possible and talk about redshift. That actually gets around a lot of problems. We use the velocity that I've been talking about so far, the one that's in Hubble's law, and this particular metric for several reasons. It describes a homogeneous isotropic universe times the proper time of co-moving observers. Synchronicity can be measured by the cosmic microwave background temperature, so we can define a common time since the beginning of the universe based on what the temperature someone measures the CMB to be, and it makes calculation simple. But of course, as you're pointing out, other metrics are equally valid, and the conformal metric, for example, is one where you have the scale factor outside of outside of time, as well as the spatial coordinates. And here you don't get velocities faster than the speed of light. You have all special relativistic sort of behavior. So yes, thank you very much for bringing that up. That's a really excellent point. I'll come back to this part, but I'll go back to exploring for a little while the implications of the metric that we usually use for cosmology. So I'll make it clear that that's what I'm doing. Okay, so let's look at what light does in this metric. So you've got ds equals 0 here. And so if you've got 0, the part of the metric that's left over is not dt equals 0 here. If you rearrange this part of the metric, you see that the speed of light is scale factor times rate of change of co-moving coordinate. So for this reason, you have the, if you look here, the part that where light is traveling is entirely in this peculiar velocity part, not in this expansion of space part. If you split it up in the way that we usually do with recession velocity plus peculiar velocity. So let's have a look at the implications of that for how light travels through space. And to do that, we'll start with a super simple space-time diagram. This is a non-expanding boring universe where, again, time is going vertically and distance is going horizontally. Since this is a non-expanding universe, you can imagine these vertical lines as the world lines of galaxies, and us at the middle. I'm doing this one just to sort of, in a very simple way, introduce the concepts of like the past light cone, the event horizon, and stuff like that. So if we're sitting at this point at the tip of this cone, the past light cone, on the past light cone are the events that we're seeing right now, and inside the past light cone events are events that we've been able to see in the past. As this tip goes up, the cone gets larger, and the events that we can have seen in the past gets bigger and bigger. If there was an end to time, so imagine there's an end to time here, then the event horizon is the limit of everything that we can see at the end of time. And so that's basically our past light cone at the end of time. Now there's two types of horizon in the universe, or at least two, relative to cosmology. The other one that gets talked about quite often is the particle horizon, and doesn't separate events on this diagram from the ones we can see and the ones that we can't. It separates the particles. So this is determining which particles we can see at a particular time. So if we're here at the moment, the particle that we can see that's just come within our event horizon is this one, the second one out. And we can see it by the light that it emitted at the beginning of time. So if I put them all back on, you can see that the light that was emitted at the beginning time that has just reached us, and that's the particle that's come within the particle horizon right now. And you'll notice that that particle is outside, in this simple diagram, it's outside the event horizon. So any light that it emits now won't reach us before the end of time, and any light that we emit right now won't reach it before the end of time. So but we're seeing it by the light that was emitted a very long time ago. Okay, so now let's put this on a real space-time diagram for the universe that we think that we live in. So this is time and distance again, horizontally. This is the co-moving distance now. I've given it units by multiplying by the scale factor at the present day. The past light cone is no longer straight. It's this curved shape. If I was in the room, I'd ask you what the reason for that was, but you can actually, I'll just answer. The reason is because the actual distances between galaxies early on is quite small. So it's easy for light to get a particular co-moving distance in the early universe because the physical distance between those 2 points is very small early on. But it gets much more difficult to make that journey later in the universe because things have moved further apart. So that's just simply a fact that the physical distances are increasing between particular co-moving separations. Now I've labeled some galaxies here. So this is redshift 1. These numbers at the top are redshifts. So it's redshift 1, 3, 10, 1,000. And once you get to the particle horizon, that would be a redshift of infinity. And what you're seeing at the particle horizon is the light that was emitted right at the very beginning of the universe has just reached us. And that's the object or particle or position in space that's just come within our particle horizon. Now, in our universe, we do not think there is an end to time. However, if you integrate over the infinite future of time, you can get the event horizon. And in our universe, since it's accelerating, there is actually an event horizon. And what you see, if you take the tip of this light cone up and drag it up to infinity in time, it will become this event horizon. So that's basically the past light cone at the end of time, which happens to be an infinite time at the moment, or in our universe rather. You can also see the Hubble sphere. The Hubble sphere is that distance equals c on h, the distance at which recession velocities are equal to the speed of light. Initially, so this is the one on h. So since h is, you can see sort of here as the acceleration and deceleration of the universe somewhat, but that might be clearer later. But the turning point here is where the turning point where we went from an accelerating to decelerating universe here, because this part really is just the expansion rate because you've factored out the scale, changing scale factor. And this yellow hashed region here is the things that are beyond our Hubble sphere at the time that the light was emitted, but that we can actually see. So these are things that are receding faster than the speed of light that we're actually going to be able to see. And so this is the answer to that question before, that just because things are receding at the answer is we can see things that are receding faster than the speed of light. So let's look at that, putting the scale factor back in and what it looks like in proper distance. You have this past light cones now a teardrop shape, and you can see that the stuff that's the photons that are outside the Hubble sphere, their total velocity, their recession plus peculiar velocity, is positive away from us, even though the photon's traveling towards us at the speed of light in the local co-moving frame. And so initially, in this coordinate system at least, the light is dragged away from us and then starts to come towards us. And the point where it starts to come towards us is where it passes across the Hubble sphere. Now, how is it possible to see things that are receding faster than the speed of light? The only reason that's possible is because the Hubble sphere is increasing in size in physical space here. Basically, the photons are being dragged away, but the Hubble sphere is receding faster than that. And so it can overtake the photons, allowing the photons to come towards us. So it's because of this increasing Hubble sphere that we're able to see things that are receding faster than the speed of light. And if in the infinite future, when we become excuse me, close to exponential expansion, or we tend towards exponential expansion, if you recall, that's the point at which the Hubble parameter doesn't change anymore. That's where the Hubble Lemaitre constant is actually a constant. And that's the point where we can no longer see anything that's receding faster than the speed of light, because that Hubble sphere is no longer receding from us. So it is not able to catch up with photons anymore. And if a photon is initially receding faster than the speed of light, it stays in that region of space and can never actually reach us. So that's when the Hubble sphere and the event horizon become a single thing, but that's only in the future in our universe. It's not currently. Does anyone have any questions on that? If you want, you can also use the Q&A in Slido and post questions in the poll there, and then you can I can try and answer those. And if someone posts a question and I don't notice it, feel free to let me know. Okay, so this is how light travels through the universe. Things can exceed the speed of light. Light can get dragged away from us. We can see things that are receding faster than the speed of light. And so what's the answer to this question here? Shine a light and how far will the light reach? The answer is it will go a finite co-moving distance, but an infinite proper distance. And so you can sort of see here that it's the same question as how far is the most distant object that we will ever see? And that in this case is something that's emitted the light from a co-moving distance of about 65 billion light years, that light comes towards us and will asymptote and never reach us if it's beyond that. And that works in the other direction as well. So there is a finite co-moving distance that light can travel. There's a finite number of galaxies that we will ever be able to communicate with. But the light that we've emitted outwards, which is basically the light, this particle horizon actually, is because the galaxies that can see us are also the same as the galaxies that we can see. It works in reverse. That goes to an infinite proper distance, even though there's a finite co-moving distance. So that's the answer to that one.
But if we want to talk to aliens, we really just care about the co-moving, right?
Yes. So in terms of communicating with people, the co-moving distance, the limit to the co-moving distance is what we really care about, because it's just a limit to the number of galaxies that we can actually ever communicate with. So your next question here, and I think I've got the generic question here again, is, so this beautiful picture, one of my favorite pictures of all time, the Hubble Ultra Deep Field. You've got lots of galaxies above a redshift of 3. How long will it take for light to get to those galaxies if we emit it now? The answer was on the previous slides, if you remember your space-time diagrams that I was just showing you. Maybe I have given it away, but let's see what you think. Okay, maybe I've lost some people because I don't have that many responses yet. Everyone's gone to sleep or declines to answer this one. There we go, we've got 14 responses. So most people are saying D.
We're quickly firing up a Python notebook to try to calculate it and get the example.
Yes. Cool, so most people so far are saying D, which I've seeded well in your brains then. So yes, a redshift of 3, if you go back to this space-time diagram here, redshift of 3 here is currently beyond our event horizon. So a redshift of 3 galaxy, we can never send light to, and we will never receive light from the present day from that galaxy. We can still see it as it is in the past, and it will never disappear completely from view. It will just get more and more redshifted and fade into unobservability, very much like what happens when someone falls into a black hole as you watch them cross the event horizon of the black hole. They don't disappear, they just fade, and their time dilation becomes so extreme that they freeze on the horizon. The same thing happens for the galaxies. The time dilation on the galaxies becomes extreme, and they fade from view, but they never sort of disappear. But we can never see something at a redshift of 3. Indeed, the distance to the event horizon now is about a redshift of 1.8. So anything beyond a redshift of 1.8, we can never communicate with, which includes the vast majority of galaxies in this picture. So the galaxies you're seeing here, most of them we will never be able to communicate with. This was a histogram I found from Muse looking at redshifts in this field. And so these are the ones that are beyond the Hubble sphere, receding faster than the speed of light. And these are the ones that are beyond our event horizon that we would never be able to communicate with. So yeah, the majority of galaxies in this picture are beyond our event horizon already, and yet we see them by the light they emitted in the past. Okay. As I said before, and was pointed out, it's really important to remember that I'm talking about velocities when I'm talking about faster than the speed of light, I'm talking about velocities velocity is Hubble parameter times distance, like in that particular equation, in the particular metric. Different metrics result in different conclusions on velocity. And this is the space-time diagram you get in conformal time, where you've got conformal time versus co-moving distance, and the light rays are restored to beautiful straight lines, and conformal time in our universe has a finite end. So the reason that there's an event horizon here is because there is a finite conformal time given the infinite time, wristwatch time that we have in our universe. Cool. Okay, so this is just the summary of what we've seen so far. Next question for you guys. I wrote an article about the expansion of the universe and redshifting of photons for Scientific American at some point. And a question that I got from like a huge number of people that read the article is, where does the energy go when photons are redshifted by the expansion of the universe? And it was not 100% obvious to me at the time what the answer was. So and the question's for you. Which one is true? You think the photons, the energy doesn't go anywhere? The photons are just being measured by galaxies that are initially receding from them and therefore appear redshifted. It's converted to gravitational potential energy because it's climbing out of a universe that was denser in the past. It's lost. We shouldn't expect that energy is conserved in an expanding universe. Or D, all of the above. So I'm very curious to see what people say on this point. Oh, this one's looking a little bit neck and neck. Not that. Oh no, gravitational potential energy has risen to the lead. We've now got 44% saying gravitational potential energy, 27% saying nowhere, 19% saying lost, and 12% saying all of the above. But we're up to 30% of nowhere and down to 40% for gravitational potential energy. So let's have a look at this question. I'm going to argue actually that the answer is nowhere, but all of the other things have validity to them as well. So let's explore this. So firstly, it definitely looks like energy is not conserved in our expanding universe. If you take a co-moving volume of space, for energy to be conserved overall, it needs to be conserved in that co-moving volume of space. So if you've got the matter density is the matter density at the present day, scaling is scale factor to the -3, as it should go down in proportion to volume. The total energy in matter, this is velocityless dust, will be constant. But the energy in radiation, because the energy density goes down the scale factor to the -4, because photons are not only diluting due to volume, they're also redshifting. That energy would decrease with time. Whereas if you have the energy density in something like the cosmological constant, because it's constant, as the universe grows in size, the energy in the co-moving volume goes up in proportion to the volume. So it's not possible to, if you have all of these different components in the universe, to conserve the energy in a volume of space in the traditional way that we would usually count here. There are fun questions to do with the what's it called? Gravitational energy stuff that we can get to as well. And moreover, Noether's theorem, which is energy conservation occurs where there's time symmetry. In general relativity, you don't get energy conserved when there's no time-like killing vector, which there isn't for our expanding universe. But energy conservation is still meaningful in general relativity. It's encapsulated in div of T mu nu, the stress energy momentum tensor, being equal to 0, which means that energy is conserved at every infinitesimal point in space. And that's sort of the answer, that energy is conserved at every interaction, every infinitesimal point, but it is just difficult to add up the energy in a volume of space. And this relates to that question that I got before about what metric do you use to choose your volume. An extensive quantity like that, where you have a volume of space, you have to choose a time slicing. And that time slicing can't be done unambiguously, which is one of the reasons that you can't unambiguously choose the appropriate volume in which to calculate the energy that should be conserved. And part of the problem with conservation of energy is just that you can't choose the appropriate volume. So if you look at the redshifting of photons, as we saw in some of those plots earlier, the relationship between velocity and redshift in special relativity is very different to the relationship between recession velocity and redshift that we use when we're calculating the velocity that's in Hubble's law. We use this integration over the expansion of space to get the recession velocity. So you'll often hear it said that the cosmological redshift is not a Doppler shift. However, if you treat the cosmological redshift as a Doppler shift that as a series of infinitesimal Doppler shifts as you go from one observer receding from the other, and you integrate over the path, essentially parallel transporting the vector as you go, you end up getting this recession velocity integral. So you can show that the recession velocity is just an integral along the line of sight of infinitesimal Doppler shifts. So in that sense, it's nothing more than Doppler shifts due to the motion of the emitting and receding galaxies. And this is very similar to asking the question, where does the energy go when a rocket loses velocity relative to distant galaxies? So when peculiar velocities decay. So if you're not familiar with this, peculiar velocities decay with time in the universe, and you can see why this would be the case. So if you turn off the rocket of your spaceship and let it drift, this one rockets off at a peculiar velocity of 500 kilometers per second. This galaxy is receding from us at about 420 kilometers per second. So when the rocket eventually gets to there, it will have a peculiar velocity of only 80 kilometers per second. The simple Galilean transform there actually works quite well because all the velocities are very slow. So this has not been an acceleration at all. It's just measuring in a different reference frame. And going back to this super simple diagram that we had before, if you want to have a galaxy that's at rest and not participating in the expansion of the universe, this is just to have a look at what peculiar velocities do over time. If it was just sitting at rest and there's no acceleration, deceleration in the universe, then early on in the universe, it would have to have a fast peculiar velocity towards us to counteract the fast recession velocity away from us. Whereas later on, it would have to have a slow peculiar velocity to have to match the slow recession velocity away from us. And so this is basically why peculiar velocities decay, because in the absence of any accelerations, just to stay at a constant distance, the peculiar velocity goes down, and it's just bookkeeping. It's just you're trading off, the total velocity is zero at the whole time, and it's just how much goes into recession velocity versus peculiar velocity. It's just because you're measuring it against different galaxies that are receding at different rates as time goes on. So it's sort of nothing more than that, really. In detail, once you include relativistic effects, it's actually the peculiar momentum that decays as one on the scale factor, which leads to some interesting effects. So you can imagine a photon can't, if this was a photon, it would be and end up moving inwards. But let me get to that, because this is something that I found just sort of really cool. If you look at how peculiar momentum decays, this is a plot of the peculiar velocity versus scale factor that one of my students made for me, Aaron Glanville. And this is just as you start at a variety of different velocities. So if you start at 0.6 times the speed of light, the velocity will decay quite quickly. But as you go closer and closer to the speed of light, you asymptote to your velocity doesn't decay at all. And so this is how particles and massive particles and photons actually have a continuum of behaviors between them. So it's not like the peculiar velocities of massive particles decay, and then there's this big gap. And if you're a relativistic particle, you don't decay. A photon, you don't decay. As you go to faster and faster velocities for massive particles, they tend towards the behavior of photons, which is reassuring. And if you look at the de Broglie wavelength of your massive particles, you can actually look at the redshift of the de Broglie wavelength. And that actually goes down in proportion to 1 on the scale factor. So that's a really cool feature as well, that if you look at the decay of peculiar velocities, it's actually the same as the redshifting of the de Broglie wavelength of a galaxy. Cool. So what about the gravitational redshift bit? Well, in a homogeneous universe, there's no gravitational gradient for the photon to climb out of. It's the same in both directions. However, this again is a point where if you change your coordinate system, you can change this description. And I think I've probably run out of time to talk about it today, but if you change what you consider a constant time and you choose a different coordinate system, then you can get things where photons are climbing out of gravitational wells, and along a constant time slice, you have a higher density. And that can change the way you interpret where the redshifting of photons comes from. So that's pretty cool. Okay, I think I've got a few more questions, but I think I'm probably butting up against the time that we have here. So I'll just probably just skip to the end and see if there's anything else I really, really desperately wanted to talk about. This is what I was just talking about, where you can change your time slicing and you can do things in Minkowski space as well and stuff. But I'll just skip to the end and say thanks very much for listening. I hope some of those questions were interesting to you all, and sort of were fun things to think about for a little while, and open the floor to more questions or comments.
Okay, well, thanks, Tamara, for a very entertaining talk. Now I know how undergrads feel when they answer clicker questions. So I don't know how we're going to do this here. It's hard for me to see who's raising a hand. I guess I can look at the participants. So why don't you raise your hand? James Taylor has a question.
Oh, yeah, I just wanted to run the last poll you were going to do on galaxy sizes.
Oh, this one here, does the expansion of space doesn't stretch galaxies because gravity holds them together?
Yeah, can we do that one?
Yeah, hi James, by the way. Hi. Yes, absolutely. I'll just open generic question for this one. I didn't buy Slido, so it limited the number of questions I could actually use. Okay, so what is this? Does the expansion of space stretch galaxies, or rather, the expansion of space does not stretch galaxies because gravity holds them together? So is that true or false? And here we're only considering the expansion of space, not the acceleration or deceleration of space. Okay, with 16 results, this is overwhelmingly true. This is, it's dropped to 89%, 90%. So this generally people think is true. And I'll be a nitpicky here, and I'll say that it's false. And that's because of the word because. And you can actually debate me on this. This is one where it's sort of ambiguous. The reason that I would say false is that once a galaxy has been formed, it does not need gravity to hold itself together against the expansion of space. Yes, it needs gravity to make it form, but once it's formed, expanding space doesn't have a force associated with it that will grab it and drag it. And so
because you're not counting vacuum energy, just sort of
that's right.
Kinetic expansion.
Yeah. So expansion itself doesn't have a force associated with it. Once pulled out of the Hubble flow, galaxies don't need any gravity to hold themselves together against expansion, but they did need gravity initially to pull them out. And I've got this chained galaxy analogy that I use, where if you've chained a galaxy and pulled it out of the Hubble flow, what happens to it once you release it? So this is like that galaxy that's free floating at an initial total velocity of 0. So it has a peculiar velocity to match its recession velocity. What happens after that? And the answer is it depends on whether the universe is accelerating or decelerating. In a non-accelerating universe, it just stays where it is. Like the peculiar velocity decays correctly, modulo some relativistic effects I won't have time to go into. But in a decelerating universe, if you release a galaxy from rest, it doesn't start to, it will rejoin the Hubble flow, but it rejoins it by accelerating towards us, passing through us, and rejoining the Hubble flow on the other side of us. Whereas if it's accelerating, it will accelerate away from us. And so the different behaviors are encapsulated here. Basically, does the Mercurial velocity decay at a rate that makes the co-moving distance, does it decay before it passes zero co-moving distance, or otherwise, is sort of the answer to that question. So without going into sort of a lot of detail on that, that was the answer. That was the answer to that question.
Okay, thanks. Do we have any other hands up? I don't see any at the moment, but any other questions? Maybe I could, related to this last point, Tamara, something I found confusing. What would you say to a student? A galaxy is really big. So isn't the space at one end of the galaxy expanding away from the space at the other, and so effectively pulling it apart?
Great question. So this is related to that, and I think some people would answer differently to this in terms of, so the answer is no, there's nothing there that would be pulling it apart. And this comes down to, what does it mean to say space is expanding? And that question before of, what is stretching the wavelength of photons? It's not anything pulling the photons. It's not like there's something on either end of the photon increasing its wavelength. It's that the photon is being measured with respect to things that are receding from it. All of our concepts of the expansion of space and sort of that we've been talking about here are in the homogeneous isotropic assumption. Once you've violated that, once you've made a galaxy that's clearly not homogeneous and isotropic, you've taken away those initial velocities. So the space around a galaxy is not expanding, and it's related to that. Matter tells space how to curve. Space tells matter how to move. Quote from Wheeler, where if you, in the absence of moving matter, or you don't have expanding space. So there's that's one way to think about it. But yeah, if you've got all of these particles that are moving away from each other, once the local gravity has won and made that little patch of the universe not expanding, it really is not expanding. There's no underlying, sort of that idea of a recession velocity that's everywhere, that's pulling apart, is a construction of our coordinate system. It's not something that's physical there, is the way I would answer that one.
Okay, still a bit tricky to get one's head around, but we're running out of time. So are there any other questions? Well,
thanks for getting up so early for us.
Yes, that's great. So what I like to ask people to do is do the hand clap for Tamara, the silent clap. We can do an actual one, but if you could put the claps on the screen, there we go. Very entertaining talk, great for undergrads. I don't know if you ever share your slides on these things, do you?
I'm happy to share slides if people would like to have a look at them. Oh, I did actually make a quick overleaf as well with all of the questions and answers for that, because that I used for something else that you can look up, which I had on the last slide, so I can share that as well. Yeah, so I know a lot of those things are sort of simple, and I'm often very nervous to talk to all the experts about those sort of things, but it's a lot of stuff that we don't often think about, so that can be sort of interesting to explore, nevertheless.
Right.
I'm still struggling over Rob's question.
Yeah, it's one.
I don't really understand.
I've done this for decades, and I still don't.
When does gravity of the galaxy cease to influence the expansion? So in other words, if you put two particles somewhere outside of the galaxy, presumably they will fly apart.
If they're near the galaxy, they'll fall towards the galaxy rather than fly apart.
So it's just a matter of when they have positive energy with respect to the galaxy, then they join the Hubble flow. Is that the way you look at it?
so if there's something near the Milky Way that's is sufficiently done by, like, attracted by our gravity. So if you put something at a constant distance from the Milky Way, I know relatively close, it will fall towards us.
Yeah.
It won't be dragged away by the expansion of space there. It will get so much velocity as it falls towards us that it will pass straight through us and out the other side. And depending on its initial conditions, it might end up going away from us and joining the Hubble flow. Sort of, its peculiar velocity will tend towards zero over time, but that peculiar velocity will tend towards zero on the other side of us. So it will come through us, pass through us, and go the other side. And that's just a relative velocity effect and the acceleration of its local area effect. So I guess the thing that we have to get away from is the concept that space itself stretches stuff. It's all initial velocities and then accelerations. It's just velocities and accelerations so if you start with an initial zero velocity with respect to something else, regardless of if all these other galaxies are receding past you, if you start with an initial zero velocity, then you'll stay there unless you're accelerated. So that's basically just the concept. If you're something positive over here, you'll be accelerated towards it. If the dominant acceleration is dark energy, you'll be accelerated away. But yeah, it's just velocities and accelerations when it comes down to it.
I'll grapple with that in silence. Thank you.
Okay, thanks, Tamara, and everybody for coming. And I gather the sun is up by now.
Yes, sun has just risen. It's looking nice outside.
Okay, well, have a good day. Thanks, everybody. Say hi to the people at UQ for me.
Will do. Thanks very
Okay.
much for having me, everybody.
Thanks, Tamara.
Bye-bye.